Okay, welcome back everyone. In this example from Chapter 5, we're going to look at a rotating system and we'll analyze the forces on a block rotating around a vertical pole. And we're trying to figure out several things in this problem. By the way, this is number 110 from Chapter 5. So we're trying to find out, first of all, the tension in the lower rope, and then we are trying to find the angular speed omega that the system rotates with. Then we are asked to find the angular frequency or angular speed omega when the lower rope goes slack. And then finally we're supposed to describe the motion of the block if that occurs. So the first thing that we should do is take a closer look at the block and look at some of the lengths. Okay, so this is actually a 3, 4, 5 right triangle with half of the pole being 1 meter. We're given the length of the string is 1.25 meters, and then that makes this radius 0.75 meters. And that's important because we're going to have a force of tension going up and away from the block, and this tension can be resolved into x and y components. And it's nice because we can write basically that the sine of our angle is opposite over hypotenuse, so just 4/5, and then the cosine of the angle is just going to be 3/5. And so we don't have to go plugging in the cosine of 53.13 degrees. This will make it a little bit easier. Okay, but let's first draw a free body diagram of the block and all the forces acting on it. So I'll do that right here. First of all, we have gravity, mg, going straight down. We have two tensions, T up and T lower, and that's pretty much it. And so what we're going to do is take those forces, and the two tensions can be decomposed into horizontal and vertical components, and I'll do that a little bit neater in a moment. And what we can do is we can apply Newton's second law. First of all, we know that the net force vertically is going to be equal to 0, and we know that the net force in the x direction is going to be, actually, if you think about it, since it's going in a circle, that's the centripetal direction. So it's equal to m times centripetal acceleration. So this problem allows us to look at centripetal acceleration as well. Okay, so let's just draw forces a little bit more clearly. We have gravity, and we have T upper and T lower. We're given T upper is 80, and so if we decompose that, I'll do that in purple. This is T upper in the y direction, and that's going to be T upper times the sine of theta. And we said earlier that that was going to be 4/5, so that's going to be 4/5 of 80, and sometimes I can't do math, that's just 64 newtons, okay? And that means that we're going to have T upper in the x direction, and T upper in the x direction is just going to be T upper times a cosine, and that's going to be 80 times 3/5, and I think that's going to give us 48 newtons. Now, keep in mind that's 48 newtons to the left, but we're going to do things in the centripetal direction. Okay, now T lower also has T lower in the y direction, and that's going to be negative T lower times 4/5, and T lower in the x direction is going to be negative T lower times 3/5. So again, sine and cosine. Okay, So, okay, so that's t lower in the x direction. Okay, so now let's do the first equation, the sum of forces in the y direction, Newton's second law, and we're going to have essentially F net in the y direction is going to be equal to 0, and let's say that up is positive for those forces, and so what that gives us is basically t up y minus t lower y minus mg equals 0. Okay, and so t upper y is 64, t lower y is basically going to be t lower times 4/5. Technically it'd be plus a negative because we have a negative here, but that's okay. And then mg is going to be, I believe, 39.2 because the mass is 4. So mg would be 4 times 9.8. So that's equal to 0. And if you calculate everything out, you will get t lower is about 31 newtons, pretty close to 31. So that's actually our answer for part A. Okay, so now in order to figure out the rotational speed, or omega, we're going to have to apply F equals ma in the centripetal direction. And now we're going to say that anything going inwards is positive. And so it turns out that we just have two components, t upper and t lower, in the x direction. So F net centripetal equals mac. Now centripetal acceleration can be v squared over r, or it can also be omega squared times r. Both of those are valid because v is equal to omega r. Okay, so now what we're going to do is write basically t upper in the x direction plus t lower in the x direction is going to be equal to m omega squared times r. Okay, and so t upper in the x direction we found was 48. T lower in the x direction is now going to be 31 times the cosine of the angle, or we could just write times 3/5, and that's going to be equal to mass times omega squared times r, and r is 0.75 or 3/4. And then if you solve that for omega, you're going to find something right around 4.71, but that's units of radians per second. And those are the units that come out if we have newtons and meters and kilograms. Okay, now we need to get this into revolutions per minute, so it's actually pretty easy to do that. We know that we have 2 pi radians going into 1 revolution, and we know that we have 60 seconds going into 1 minute, and so all of our units will cancel nicely, and so this omega will be about 45 revolutions per minute, 45 RPM. And there's our answer to part B. So now, part C says, what is omega when the lower rope goes slack? So we have to interpret what that means. When the lower rope goes slack, that's the same thing as saying t lower tends to 0. So we can just take our same equation here and rewrite it and say 48 plus 0, because t lower tends to 0, is going to be equal to m omega squared times r. Okay, and for this we get that omega is exactly the square root of 16, or it's 4 radians per second. Doing the same conversion as above, this turns into 38.2 revolutions per minute. So notice that when the lower rope goes slack, we actually have a lower rotational speed. And hopefully that makes sense, that the inertia of the mass would tend to move it to the outside of a circle. Objects in motion want to stay in motion. And so actually what happens is, as omega decreases, the angle of T upper with the vertical, will actually decrease. Because if you think about this, the limiting case is that omega is equal to 0. In that case, the block wouldn't be out at all, and the angle with the vertical would be 0. Okay, so hopefully that was of some use. We kind of put together a lot of different ideas, and next time we'll look at energy and a double object system.